Good morning. Happy Friday. Today is day 133, and today we're going to continue focusing on what we started yesterday. That's going to be solving linear systems by substitution. So all week we've been focused on linear systems, understanding that a system of linear equations is two or more linear equations that we deal together at once. And we've been working on finding the common solutions, or the solution that works for both equations in our linear system. And our method the last couple days, what we introduced yesterday, was a method called substitution, where we're going to replace a variable with a number that it's equal to, or we added to this definition in 8th grade an equivalent expression. Sometimes we know y is equal to 2x, and we might plug in 2x for y instead of just a number. If you think back to last year, this is really the plug part of plug and chug. At this point, hopefully you've read through today's objectives and key terms. I would encourage you to take a look at those again. We're going to jump right to step 3, which is after you've completed today's work on your own for the purple box problems or the exploratory problems, you're analyzing your work through this video. So the first problem today for Explore Problems, problem set A, we were given a linear system or a system of linear equations. The first equation in red was y equals 3x, and the second equation in blue was 4x plus 2y equals 30. Our ultimate goal is going to be to find the common solution to this linear system again. Our method today is going to continue to be substitution. And part 1 asked us, what information does the red equation tell us about the y variable? And then they want us to explain how that information could help us transform or change the purple equation in a helpful way that could help us determine the common solution. So the big thing to recognize, if we focus on this red equation and what it tells us about the y variable, we see that y, a statement, y has to be equal or is equivalent to the term 3x. This isn't as helpful as knowing what number y or x will be to start the problem, but if we know y is equal to 3x, how can that help us transform the purple equation? We're going to take a look on the whiteboard and then answer part 1 and part 2 together. So if we take a look at the whiteboard, I'm going to put this in full screen. The red equation and the blue equation are up here. If we know that y has to be equal to 3x, we can take this 3x, a block that's equivalent in weight or the same value as y, and we can replace y in the purple equation with that 3x. Because y and 3x have the same value, and an equation is just a statement about balance, the left side has the same value as the right side, we can replace y with something that has the same value, substitution, and it's still going to be a true statement. So if I take this equation and the y, I'm going to use parentheses whenever I'm substituting. This is a complicated process. The parentheses help me know I'm multiplying and what's getting multiplied by the two. 3x gets replaced or plugged in, as Mr. Neville would say, for the y into this equation. The rest of the equation is going to be unchanged. We still have 4x, and it used to be 2 times y. We replace y with 3x, so that 3x still needs to have a coefficient or a multiplier of 2. All of that's still going to be equal to 30. As you're thinking about your explanation for part 1, we should understand, and I'll leave you on your own to see this, why going from this first starting equation in purple, how we transformed it, why substitution was helpful there. We'll go ahead and solve this equation out now. First thing I'd be doing if I see 2 times 3x, I would simplify or evaluate. Recognize that's 6x. And at this point, we see there's still 2 terms with a variable, but now they're like terms. They're both x's. So I can simplify the equation by combining them. 4x plus 6 more x's gives us 10 x's. I would be solving this last step by inspection. I know the number 3 times 10 gives us 30, so I can go ahead and solve the equation, say x equals 3. If I wasn't sure, I could have divided both sides of the equation by 10, because that's the inverse operation, or the opposite of timesing by 10, and that would cancel it out. A lot of work, but now we see half of our common solution. If I'm going to try to find the common solution here, which we'll put that here, I know the x half of my common solution is now going to be 3. Once I know that x is 3, finding the other half of the common solution is a bit easier. I'm going to look back to the original equations. Purple's kind of complicated. Red is ready to tell me y immediately. It says y will be equal to 3 times whatever x is. So I'll take the 3 for x, plug it in here. Y equals 3 times 3. Or y is going to be equal to 9. If I want to confirm that this is the common solution, and we're going to show this in part B, I would plug in the 3 for x. 4 times 3 would give me 12. And I would plug in the 9 for y. 2 times 9 would give me 18. And we see 12 plus 18 really does give us 30. 3 for x, 9 for y is going to work in both of these equations. At this point, what we're going to ask you to do, before you continue watching the video, if you struggled with part B, if you didn't get part B on your own, there are 2 options. Option 1 is to actually start doing some of the practice problems. So if you take a look here, you are ready at this point to do practice problem number 1, practice problem number 2, and would encourage you to start doing those now, maybe before you come back and work on practice problem B, explore problem B. In this video, we're going to continue going through Explore Problem B. The second part here, it's a pretty challenging linear system, and that's going to help prepare you for some of the tougher linear systems that come at the end of the practice problems today. So again, feel free to pause this video, start working through the first 2 practice problems, and then you can come back, watch this video, and work on Explore Problem B a little bit later in class. All right. We're going to switch gears now. We're going to take a look at Explore Problem B. In the interest of time, it's a linear system, so we're just going to show you how to solve this more complicated linear system. They ask us to use substitution to determine any common solutions again, so that's been our strategy the last couple of days. We're going to try to replace one of the x's or y's to get it down to a 1-variable equation. Here, and we'll full screen the whiteboard because it's got both equations already. What we recognize, the first equation is complicated, but it says x is equivalent to this expression, 2 times y minus 4. So whatever x is, we don't know that yet. It has to have the same exact value as the expression 2y minus 4. That could help me over here in the purple equation, because if I know x and the expression 2y minus 4 all have the same value, I could actually go over here and replace this x with 2y minus 4. That's going to make the equation look more complicated. I'm going to use parentheses again. That's a key for substitution. Using parentheses helps indicate this x, whatever's replacing it. This whole expression has to be multiplied with the 3. I still have negative 4y. That still equals negative 6. So as we plugged in the 2y minus 4 for x there, it made our equation look more complicated, but now it goes from an equation with 2 different variables, x and y, to an equation that only has y's. Earlier this year, we worked with the distributive property, something Mr. Neville introduced, and we solved equations that looked like this, and now we see maybe why we had to get that skill, because linear systems that are complicated lead to something that's in the distributive property or the factored form that we need to put into expanded form. So hopefully you remember, multiply that 3 out with every term in here. 3 times 2y is 6y. 3, a positive 3 times a negative 4 gives us a negative 12. Minus 4y equals negative 6. The river is helpful here. It helps me recognize that even though my constants, the negative 12 and the negative 6, are on different sides of the equation, my 2 variable terms, 6y and negative 4y, are on the same side of the equation. They're gathered already. 6y's minus 4y's gives us 2y. The negative 12, the equal sign, the negative 6, of course, just come down as we're simplifying this equation by combining like terms. Hopefully this should be peeling the onion. If you're still a little bit stuck peeling the onion with Mr. Neville last year, we see the y terms are now gathered on the left side. We need to get rid of the negative 12 first and then the coefficient. So to get rid of the negative 12, we'd add 12 to both sides. 12 minus 6 leaves us with a positive 6. That's equal